Okay, so let's finish with yet another result about non-computable models. And then we'll talk about more effectiveness properties of computable structures. And then, if I still have time, I will go back to decidable structures and tell you what I forgot to tell you about them. Okay, so we have seen examples of decidable structures, of computable structures, of non-computable structures. The question is what degrees we may at all realize as degrees of structures. And well, the thing is that the result that I want to show you, well, the last one about this topic is the result that degrees of a structure are closed upwards. So if we know that we have a presentation of a structure of some degree, then in all non-trivial cases, whenever we have a degree that is above our degree, there will be also a presentation of this degree. Okay? So this is in general a non-trivial result, but we will only prove it in a simple case when the structure contains a linear order. Okay? So let's formulate the theorem first. In all non-trivial cases, and this non-trivial is actually there is a formal definition of this. What this non-trivial mean? A trivial structure is a structure that is, very trivial. So if we fix some finite number of elements, all other elements can be sent to each other via an automorphism. Okay, so those are structures, like a complete graph or something like this. So only not interesting cases, and everything that is a bit more structurally a little bit more complicated will be already non-trivial. So all non-trivial cases, if there is a presentation of a structure that is, let's say, of degree D, and we have some other degree, let's say C, that is above D, then there exists a presentation of the same structure of degree C. Okay. So, proof. As I said, we only consider the case where A has whatever set, and then a linear order. This is a linear order, and then maybe something else. Okay. So how do we build a new presentation? A new presentation. So, we will need. Let me see. We'll build some B, a new presentation. And okay, let me check. Okay. So let's say A was the set A0, A1, and so on. And the set B is the set B0, B1, and so on. And well, we define a one-to-one function. F is a one-to-one function from A to B, and it might switch. So it will send the pair A to n, A to n plus 1 to a pair B to n, B to n plus 1, but it might switch the order. And this switch in the order will depend on the set X, where the set X is the set of the degree C. Okay, so we say that n belongs to X if and only if in A we will have f minus 1 b to n is less than f minus 1 or b to n plus 1. So, yeah. So this just means that if, if n is in X, oh, let me see, I'm confused here a bit. So in one situation we switch them, in the other situation we do not switch it. Okay, so that's what's happening here. And then by doing this we introduce this slight permutation maybe of this universe that will correspond to this linear order, and then all the other like interpretations of all the other symbols are just pulled back, defined in the natural way, just to have the isomorphism here. Okay, so if I had something here, some R hold on some element here, so I pull them. So using this function f, I define it as true on those elements here. Okay, so and yeah, for linear orders, this is pretty much it. Yeah, so this is exactly how we code it, and so formally we need the set X and also A to be able to compute our B, but A is of degree that is less than X. So this is using X, we get everything that we need. Okay. In general case, when we do not have a linear order, the proof is longer, more complicated. Okay, we do not do this. Okay, so now let me first correct myself. I said here that this is not decidable. Of course, this can be decidable, but now we will see a copy that is not decidable, and it will be very useful for further considerations. So let's consider this structure. Oh, so omega and the linear order. Okay, just the natural linear order on the natural numbers. So we have 0, 1, 2, 3, and so on. So this is our decidable copy, actually. Yeah. Let's say L0. And now let's consider another copy. So we'll take the even numbers and put it in the same order: 0, 2, 4, 6, 8, and so on. And then we will use odd numbers to make this structure it will be still computable, but not decidable anymore. So we take, let's just say we take the halting set and we compute, so let's just take the set K, take the set K, the computably enumerable, not computable set, the famous thing. And then we enumerate it. And let's say we have some X enumerated into the set by the stage S. Then what we do, we find the place where this is, let's say, this is 2x, so my x is 2. Let's say x is equals 2, and let's say it enters k at the stage 17. Okay? So, no, let's not take 17, it's too much. Let's take 3. Okay? So we find this spot here, and between 2x and 2x plus 2, we put 2 times s plus 1. Okay, so s is for 3 here, so this is 2 times 3 plus 1. And we can assume that at each stage something enters, so we will actually use up all the odd numbers. So the universe will be still omega, but between some elements between some even elements we will have odd elements, between some others we will have no odd elements, which will mean that, for example, 1 is not in K at any stage, so here will be nothing. So 4 will be a successor of 2, but 6 will not be a successor of 4. Okay, so, and this is still a computable structure, because after finitely many, so we build it step by step, so after finitely many steps, we will define all the order. And this is important. This is a linear order, so it is not a successor function. It is not a situation like this. In a situation like this, we wouldn't be able to break it and put an element here. But this is just a linear order, so we can actually put as many elements in between as we like. Okay, so we put 1 or none. Okay, and these are 2 computable copies of this linear order. They are obviously isomorphic, but the isomorphism is not itself computable. So to compute the isomorphism between these 2 copies, we need to know whether there will be something in between or not. So we need one jump to be able to do this. In a computable way, we cannot do it. So from like structural point of view, from algebraic point of view, this is one and the same structure. From computability point of view, effective point of view, those are very different. Okay? Because we have this difference. So there is an isomorphism, but no computable isomorphism. Let me give now a definition. If we do have such a computable isomorphism, then this such a structure is called computably categorical. So a structure A is computably categorical if every its computable isomorphic copy is actually computably isomorphic. Okay, so computable categoricity is meant to remind somehow countable categoricity or whatever. Yeah, so here we have just one copy of a computable structure up to computable isomorphism, provided that we from the very beginning are already looking at isomorphic copies. Okay, so in particular, if we have, let's say, the standard model of Peano arithmetic, or any model where we can, from the very beginning, fix the first element and the successor function, this will be computably categorical. Okay, just because we map 0 to 0 and the rest follows. Okay, so this is not computably, this one. Not computably categorical, but it is zero jump categorical. Okay, so, and this is the question. If a structure is not computably categorical, what is the degree, or what are possible degrees that could compute an isomorphism? So there is quite a lot of research in this direction, finding the most optimal degrees, if there exist any, or proving that there exist no such optimal degrees, like the least degrees, minimal degrees that can do it, and so on and so forth. So, okay, what else can I tell you here about this computable categoricity? Let me check to do it in the correct order, and not forget anything again. Okay, so what else can we have? Let's consider another example, an example that we also had already. An equivalence structure, omega, an equivalence relation with infinitely many classes of size 1 and infinitely many classes of size 2. What do you think? Is it computably categorical or not? What do you think? There are only two options. Okay, so let's see. You remember we had this copy where this was 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So let's try to build a computable isomorphism. So this is our nice copy A, and this is another copy B that someone gives us. And we need to build the isomorphism. Okay, so those elements will appear in some order, step by step. And as soon as they appear, we will know that, okay, this is not related to this is not related to that, maybe this is related to this, and so on. Okay? So, okay, as soon as we have this kind of situation, we know this is an equivalence class of size 2, so then we just do something like this. However, if we have a situation where we have a class of size 1, one point that is not related to anything. So we think, okay, this is an equivalence class of size 1, probably. So we attempt to do something like this, and then the structure says, oh, you know, this is actually a size of class 2, just this element have not yet appeared. Here it is. So this is a size of class 2, class of size 2. And so by doing this, our isomorphism is destroyed. Okay. So this is not computably categorical. But again, with the zero jump, we can do this. Because with zero jump, we can ask what is the size of my class? Is there anything that is related to this element or not? Okay, so zero jump categorical. Okay, so actually in both this situation and this situation, we can find infinitely many structures that are computable, isomorphic to our structure, but not computably, pairwise computably non-isomorphic. Infinitely many computable, pairwise non-isomorphic, non-computably isomorphic. But in general, isomorphic copies. Sorry, it's not A, it's S. Oh, well, it's A, it's a copy. Okay, so this is the situation we have now. Either we have one copy up to isomorphism, up to computable isomorphism, or we have infinitely many copies after computable isomorphism. The question is, can we have something more than that? And again, this might, well, one might consider it as some kind of effective counterexample again to the same Watt's theorem. Yeah, that we might have also two as like we might also have exactly two computable, not computably isomorphic, not computably isomorphic copies of whatever structure. So actually for any, so this is called computable dimension. Yeah, the number of non-computably isomorphic computable presentations of our structure. This is computable dimension. And natural computable dimensions are 1 and omega. And this is result by Goncharov, also from the 70s, I think, that actually any natural number is possible as computable dimension. Any n is possible. Okay, and the way he proves it, it's the usual way to prove this kind of results, especially back then it was, and especially characteristic for this Russian school where a lot of numberings were used. So first you construct some family of sets with some particular properties using priority constructions and things like this, and then you code this into structures. Okay, so that's what he did. He built a family with some specific properties on the numberings, that there were just two nice numberings that were not equivalent to each other, let's say for the case of 2. And then he coded it into the structure. So I will not talk about the proof. I do not want to lose you discussing priority constructions. Okay, so I said that in natural cases we have this situation. Theoretically, of course, there are ways to code those artificial structures as, I don't know, some more or less structures, some more or less natural classes, like maybe some kind of graphs or lattices or even groups or something, but those structures still will not be really natural themselves. Okay, so those will be still artificially constructed structures. Okay. Fine. So this is actually a question: is there a natural example of a structure of a computable dimension, some finite n greater than or equal to 2? Okay, so fine. So maybe if we talk about natural structures, just let me mention that for some classes we have a characterization when a structure is computably categorical. Like for example, for linear orders, linear order is computably categorical if and only if it has finitely many adjacencies. Adjacencies. I don't remember how to spell adjacencies. J and C's. Okay, that's what. Okay, you know what I mean. Okay, Boolean algebras are computably categorical if and only if they have finitely many atoms. There is also a description for equivalent structures. It is a bit longer than that, but it's also in terms of sizes of classes that they must have, I don't know, finitely many finite equivalence classes or finitely many infinite classes, and the sizes of finite classes must be bounded, and there must be at most one class that has like finite size, and there must be at most one k that we have infinitely many classes of this size k. Yeah. So description also exists. I'm not sure I want to write it. Okay, so algebraically closed fields also, if they have finite transcendence degree, then they are computably categorical. Otherwise, dimension infinity. Okay. Fine. So algebraically closed fields. Okay. So for some classes, of course, we have no such characterizations, like, and these are classes that are universal, like, that everything can be coded into them, like graphs. No way we can describe what kind of graphs are computably categorical. Okay. So still it is a question: how can we, like, we want to have some kind of description, some kind of syntactic characterization of this property, yes, of this computable categoricity. It's a nice property when you have some syntactic conditions that will ensure that the structure is computably categorical. Okay. Syntactic description, syntactic characterization. Computably categorical structures. This is what we want. Well, there is something in this direction. Something in this direction, which involves so-called Scott families. So a Scott family for structure for structure A is a set, well, let's say we only concentrate now on characterization of computable categoricity. So already in the definition of this Scott family, I will fix the complexity of those formulas, of existential formulas. Whatever, phi 0, maybe with finitely many parameters, some fixed parameters, and then let's say x0, x and 0, and then phi 1, the same set of parameters a, and then x0, x and 1, and so on. So existential formula such that every tuple of elements from A satisfy one of those phi's. B of whatever length from A, some length, satisfies one of those phi's. And if two tuples satisfy one and the same formula, then there is an automorphism of the structure that sends one to another. If B and C from A are such that we have phi of A, B, and phi of AC, then there is an automorphism of A that sends B to C. Okay, so basically those formulas, those existential formulas, completely describe us the orbits and the automorphism of all those tuples. Okay. Possibly with whatever parameters A that we need. Okay, and if we have, if a structure has such a family, then it is computably categorical. So claim, let's say proposition, if A has a Scott family, then it is computably categorical. How do we prove it? Well, basically we prove it stage by stage. Okay, so suppose A is our structure, and suppose our family looks like this. Yeah, so this is V0, V1, and so on. And those are my parameters. And suppose I have two computable copies of A, A1, A2 are computable copies. We built an isomorphism, a computable isomorphism between those A and B, A1 and A2. So we build it stage by stage. Let's say stage 0. We just look how those constants are interpreted in both of those structures. So those are finitely many fixed constants. So we just, first then we just say, okay, we map them in the correct way. And so our phi0, like the isomorphism F at the stage 0, will contain those pairs. So we send A0 in the first copy to A0 in the second copy, A1 from the first copy to A1 from the second copy, and so on. A, whatever it is, K from the first copy to AK from the second copy. Yeah, so we just define from the very beginning that constants, those distinguished constants, go in the correct way. And then we will distinguish between even and odd stages. Yeah, at even stages, we will increase the domain and find the corresponding image. And at so what was it? At odd stages, and at even stages, we will do the other way around. So we will get some new element in the image, and we will make sure that we have some pre-image for it. Okay, so stage 2k plus 1. So what do? Let's say we take a new element B, C is at B. Yeah. Let's say it is. So this is stage S. So it will be a new element BS. Yeah, and we will extend our F. So we assume that at the previous stage we had Fs plus 1 already containing all of those. And then already some pairs B1, D1, BS minus 1, DS minus 1. So this is what we have already built. And now we take a new element that is not yet anywhere here, and we want to find a corresponding DS for it. Okay, and we do it using our Scott family. So we take this tuple B1, B2, BS minus 1, BS. Okay, so this is a tuple. It satisfies some existential formula from the Scott family. Yeah, so we take this formula. This is some phi A B1 BS minus 1 BS. Okay, so what do we do from this formula? From this formula, we take the formula which is there exists an X phi of things like this, an X. Okay, so this is an existential formula which was made from this formula. It is true in A1. A2 is isomorphic to A1, so this also must be true in A2. Under this isomorphism, with these here, so this is true in A1. So in A2, phi is true in A. Okay, these are A1s, these are A2s. d1 ds minus 1 x, and yeah, that's it. We take the image of it, or we take the witness, we take the witness, and this will be our ds. Okay. Let's see. Yes, probably we need it. Yes. Yes, computable. Is a computable. What's a computable sequence? Yes. Otherwise, you will not get it. Otherwise, this function f will not be computable. Okay. So if we have a Scott family, then we have computable categoricity. Unfortunately, the reverse doesn't always hold. Yeah, so they exist. Theorem by Goncharov. There exists a computably categorical structure without a computable Scott family. Okay, and the way he does it is again the same. So he uses actually an result by Selivanov. The result says that there exists a family of sets, and this family is discrete but not effectively discrete, meaning that those sets, each of those sets, are described by some finite subset. So in each set, there exists some finite subset that is included only in this set. Yeah, so this means discrete, but not effectively discrete. So you cannot find this finite piece that characterizes the set effectively. Okay, and then you code it again into the structure, and being discrete ensures that the structure is computably categorical, and being not effectively discrete ensures that there is no Scott family. Okay, and then you can, extend all of these, go wild, and talk about like some kind of Scott families of higher complexity. Like, what if we take not existential formulas but something else? And this is actually useful. I will not talk about this because in this situation we need already infinitary formulas. But what I want to say is that this having Scott family does characterize some kind of property that is related to computable categoricity, namely relative computable categoricity. The structure A not necessarily computable, whatever countable structure A is relatively computably categorical if for any its isomorphic copy which doesn't have to be computable either, just whatever countable copy. There is an isomorphism computable in in A plus B, meaning atomic diagrams of A and B. Okay, so if we know atomic diagrams of A and B, then we can compute the n isomorphism between those. Okay, so relatively computable categorical is a stronger notion than computable categoricity, in particular because of this. So this practically shows that there exists a structure that is computably categorical but not relatively computably categorical. The reverse always holds. If we have a relatively computable categorical structure, then it is always computably categorical. Okay, and then we can also ask what happens if a structure is not relatively computably categorical, but relatively computably categorical yet up to some oracle. So if we add some more oracles here, yeah, and this is when changing these to other complexity of formulas becomes useful. So relative computable categoricity, this is a property that can be very nicely described using these syntactical terms, using Scott families. Computable categoricity is a horrible notion. And it's very natural and nice looking, but syntactically seen is very complicated. Okay, so that's it. What I wanted to tell you about computable structures. I don't know. I have 10 minutes. If I want to go back to this, I'll just tell you more, some kind of overview. What else happens in computable structure theory? Maybe let's go back. Yeah, let's go back. I will just give you another couple of results that I wanted to tell you, and show this effective version of Watt's theorem. You know, something that one can consider as an effectivization of Watt's theorem. Okay, and it has to deal with this topic that I want to talk about is about atomic and saturated models of a theory. Yeah, so those are natural model theoretic notions. Yeah, let's say we have prime models and we have saturated models. Yeah, a prime model. Prime model of a theory T. This is just a model that elementary embeds into any other model. Yeah, so this is the simplest model theoretically seen model of the theory T. And there is another notion that is equivalent to this one: atomic models. Atomic model. Those are those that realize only principal types of the theory. And prime models, well, it is the same countable atomic model. Okay, so in this countable situation, which we are in, we consider only countable models. Prime and atomic is the same. Okay, so this is a classical result. How does an effectivization of this result look like? So suppose we have, it's also again, I think Goncharov, maybe someone else on the Western side. Yes, Harrington. Goncharov, Nurtazin, and Harrington. They proved that a complete decidable theory has a decidable prime model. Has a decidable if well, if there is a computable function taking, if there is computable function taking each formula to an index of a computable type, isolated type that contains this formula. There exists a computable function taking each formula to a principal type containing this formula. So this is basically an effectivization of saying that prime models are atomic models. Yeah, so we have a decidable prime model if and only if we have an effective way of those principal types. Okay, so when the proof is a priority construction, it is a mix of a Henkin construction. So we have several steps, and we have two kinds of requirements. The first requirement ensures that we build a decidable model of this theory using the Henkin construction, and the other kind of requirement says that all the types, like if we realize some type, then it must be principal. And this second kind of requirements, those are requirements that can be somehow violated, and then we need to set some priority and do some work on this to be able, but it's possible to do it. Yeah? So it's not a very complicated construction. Must still require some work. Okay, so this is for prime models. For saturated models, saturated models are those that realize all the types of the theory, and the result is, again, by Goncharov and Morley and Miller, three of them independently. So a decidable theory T has a decidable saturated model. If and only if the types of T are uniformly computable. Computable. Okay, and this is quite easy to see actually that this holds. Okay, so the question now is, so we have a decidable theory and it has, let's say, decidable, what can happen? That it has a decidable saturated model but not decidable prime model but not decidable saturated model, and so on and so forth. And result also by Yershov says that if a decidable theory has a decidable saturated model, then it has to have a decidable prime model. Okay, so it cannot happen that the saturated model is decidable, and I will not give the proof. I have no time for the proof. Okay, so then I just formulate this effective Watts theorem and show you how it follows from this result. So effective Watt's theorem says that if we have a complete theory and it is not countably categorical, if T is complete, not countably categorical, and has a decidable saturated model, then it has at least 3 non-isomorphic decidable models. And well, this saturated model is the first one, the prime model is the second one, and the third one you get from the classical proof of Watt's theorem. Yeah. So because everything is decidable, the theory itself was decidable, everything is very, very effective, so the third model will be also decidable. Okay, so I had some more things to say, but I think I'll stop here. Thank you. See you tomorrow.